Bismillahirrahmanirrahim. Assalamu alaikum dear students. This is our next problem. Problem having been chosen from the same book, Modern Physics by Paul A. Tipler. As usual, we first come to its statement. Okay. The work function for cesium is 1.9 electron volt, the lowest of any metal. Part A, find the threshold frequency and wavelength for the photoelectric effect. Find the stopping potential if the wavelength of the incident light is part B 300 nanometer, nano standing for 10 raised to the power minus 9. 300 nanometer, part C 400 nanometer. Okay. So in part A we have to find out two things: threshold frequency and threshold wavelength, while in part B and C we have to find out potential difference, while wavelengths given are different from the wavelength which we have to find out in part A. Okay, in part A, threshold frequency and threshold wavelength are to be determined, and this wavelength will be different from these two values, that is 300 nano, that is to say threshold wavelength which we will determine in part A will neither be 300 nanometer nor 400 nanometer. Okay. Moreover, dear students, before starting its solution, it is important to point out here that sometimes we use the term cutoff wavelength and cutoff frequency. Okay. Cutoff and threshold are to some extent synonymous terms, but they are not exactly same. If we go in detail about their philosophy, we see enough difference between these two. Okay, so we can say that cutoff frequency and cutoff wavelength versus threshold frequency and threshold wavelength, there is a similarity as well as a difference between these two. Okay. However, it is important to point out that these two terms go side by side. Okay. Now we are going to its solution, but as with other problems, as with other videos, first before starting its solution in a proper manner, we will have to go through a few snapshots which will provide a foundation regarding the solution of this problem. Okay, so in this problem we will meet about four snapshots. Okay, four snapshots. Dear students, this is the first snapshot which is concerned with the solution of this problem. This is a table of physical constants. We will not go in detail about this snapshot because this table has been used so many times in our previous problems, previous videos. So we will take that value which we will require. Okay, anyhow, now we move to next snapshot is the table of photoelectric work functions. Here cesium comes in second row, second serial number. Okay, cesium CS 1.95. It is quite clear that amongst all these values 1.95 is the smallest, and this fact has been emphasized or made more clear in the statement that this is the smallest of table of work functions of various elements. Okay. Moreover, dear students, we once again go to the statement. Okay. In this statement, work function is given as 1.9, while in the table which we have introduced here work function of cesium is given as 1.95. Okay, dear students, actually here this table is not necessary to display, but it is just displayed in order to make sure that even if the value of work function of cesium is not provided in the statement, we can take this value from such tables which are given in almost every book on physics. Okay, so moreover, dear students, moreover, value given in the statement is 1.9, that is 1.90, while in the table it is given as 1.95. So we will not consider this. Okay, we will give preference to the value provided in the statement, which is 1.9. Okay, because when we put 1.90 or 1.95, a considerable or small difference will appear, and in such cases we have to prefer the value provided in the statement. So we will take the value of the work function of cesium as 1.90 instead of 1.95. Next snapshot is about photoelectric effect. Photoelectric effect, EV naught is equal to HF minus phi. Okay, here E is the magnitude of electron charge. Okay, magnitude of electron charge or magnitude of proton charge, same thing. Okay, moreover, V naught is the stopping potential, H is the Planck's constant, F is the light frequency, and HF combinedly is called the energy of absorbed photon. Okay, similarly, EV naught combinedly is the maximum kinetic energy of photoelectron. Okay, combinedly maximum kinetic energy, and individually or separately magnitude of electron charge and stopping potential. Similarly, combinedly energy of absorbed photon, while individually Planck's constant and light frequency. Similarly, phi is the work function. Dear students, next table is the table of Greek alphabets. Purpose of this table is just to ensure that we are pronouncing Greek alphabets rightly. Okay, here this symbol is called phi. Okay, this phi, yes, phi. This symbol is called phi, and psi is also to some extent similar to this. Okay, similarly, in our previous video, in which black body radiation, Stephen Boltzmann law, Wayne displacement law was under consideration, this Greek alphabet was used, which is called sigma or summation, and I had rightly pronounced it as sigma or summation, but I was not very sure in our previous video or previous problem. Okay, anyhow, purpose of this snapshot has become more appropriate, because here pronunciation of Greek alphabet phi is also made clear, and sigma or summation, which was used in our previous problem, has also been checked or clarified. Okay, next, some introduction about work function is given. Dear students, we will not go in detail because we have explained this snapshot in previous problems, so we'll skip for the time being. However, it is important if students want to give some time to this definition or explanation about photoelectric effect. Okay, now we are going to start our solution in a formal manner. Part A. Okay, part. We know that threshold wavelength is given as lambda t, where t stands for threshold. Here t can also be replaced by c, which will be called cutoff wavelength. Okay, but here we are concerned with threshold. Okay, so lambda t, that is threshold wavelength, is equal to hc over lambda. Using hc equal to this. Okay, dear students, the table of physical constants which was shown as a snapshot number 1 in this video, in this problem, a number of physical constants were shown in that table, and in that table value of Planck's constant h separately was given, value of speed of light c separately was given, and combined value of hc was also given. Okay, so it is a facility for us that despite multiplying the value of Planck's constant h with the speed of light c, we combined multiplied value of hc is also provided in that table. Okay, so we have taken this value, that is 1240 electron volt into nanometer, from that table, which has been included as snapshot number 1 in this video. Okay, next, phi work function of cesium, which is 1.9 electron volt. Okay, this 1.9 is provided in the statement, while the table which we have shown as a snapshot in this problem as a supporting table, its value is given as 1.95, but here we are not taking 1.95, we are taking 1.90 because 1.90 is provided in this statement, and we must prefer the value given in the statement, whether it slightly differs from same value given in some other authentic source. Okay, so dear students, using hc equal to this and phi equal to this in equation number 1, we get threshold frequency lambda t equal to this over this. Here electron volt will be cancelled with electron volt, and our answer will be in nanometer, that is lambda t threshold frequency, threshold wavelength lambda t becomes equal to 652.6 nanometer. Now we are moving to part B of this. No, yet not. Now also lambda t, as lambda t is equal to hc over work function phi, this implies that work function phi is equal to hc over lambda t. This implies that c over lambda t is equal to frequency. Okay, because we know that frequency and wavelength are inversely proportional to each other with the involvement of speed of light. Okay, frequency is equal to c over wavelength, while wavelength is equal to c over frequency. Okay, so here c over lambda t will be replaced by ft, that is threshold frequency. So from here, if we keep threshold frequency ft on one side, then h will be divided on work function phi. Okay, so this implies that threshold frequency ft becomes equal to work function phi divided by Planck's constant h. So we will put both these values. Okay, upper value has been taken from the statement rather than from the table in which it is given as 1.95, while denominator value, that is value of Planck's constant h, has been taken from the table which has been included as a snapshot number 1 in this table. Okay, It is further important to point out here that value of Planck's constant in this table, which is included as par, which is included as snapshot number 1. Value of Planck's constant has been given in two different system of units. Okay, and we have chosen one out of those two. Okay, so one is that in which electron volt is involved, and other is in some other units. Okay, anyhow, out of those two values of Planck's constant, we have chosen one value, which is 4.136 into 10 raised to the power minus 15 electron volt into second. When we have put both these values in this expression, electron volt will be cancelled with electron volt, and our answer will be only in 1 divided by second, 1 over second, that is second inverse. We know that second inverse or hertz are equal. Okay, hertz unit of frequency is equal to 1 over second, that is second raised to the power minus 1, that is second inverse. So threshold frequency finally becomes equal to 0.459 into 10 raised to the power 15 hertz. Okay, our answer is correct to this extent, but just as a fashion or as a matter of discretion, we convert it in whole, not whole number. In place of 0.459, we convert it in 4.59. By doing so, 10 raised to the power 15 will be reduced to 10 raised to the power 14. Okay, so both these answers are acceptable. However, subsequent is relatively assumed better. Okay, now we are coming towards part B. We know that maximum kinetic energy of photoelectrons is given by E max equal to EVS equal to HF minus work function phi equal to HC over lambda minus phi. Okay, where Vs is the stopping potential. Okay, Vs is the stopping potential, H is the Planck's constant, F is the frequency, phi is the work function, C is the speed of light, lambda is the wavelength. This implies that EVS is equal to HC over lambda minus phi. Okay, so in the next step we are just putting the values. Value of HC has been taken from snapshot number 1, in which separate value of Planck's constant H is also given, separate value of speed of light C is also given, and in addition to these two separate values, combined value of HC is also provided, and we have taken that combined value from that table. Okay, similarly, value of wavelength lambda is provided in the statement 300 nanometer. This is quite different from that which we have calculated in part A. Okay, in part B there is 300 nanometer, in part C there is 400 nanometer wavelength. Okay, minus work function phi is 1.90 electron volt instead of 1.95 electron volt, which is given in the table which has been included as a snapshot, helping tool. Okay, so dear students, here nanometer will be cancelled with nanometer, and our answer will become electron volt minus electron volt. Both have same units, so both will be subtracted easily, and hence our final answer will become E into Vs equal to 2.23 electron volt. From here, if we divide both sides by E, we get Vs equal to 2.23 volt. Okay, because 2.23 electron volt is equal to E into Vs, while we have to calculate simply Vs, stopping potential. So stopping potential will become equal to 2.23 volt. Okay, now we are going to part C, which will be just a repetition of part B with slightly different values. Okay, so we will give less time to part C in comparison with part B. Okay, because there is just a difference of value wavelength lambda, which is instead of 300 nanometer, it is 400 here. Okay, so we know that maximum kinetic energy of photoelectrons is given by this where V is so. Okay, so our stopping potential finally becomes equal to 1.2 volt. This is the end of our problem. This is the end of our video. Till next video, Allah Hafiz.